Thank you very much. Uh, Thank you very much, first of all, for inviting me to give the seminar. Actually, as I was saying, this is the first time I've given a seminar with a split date line of this kind, which is a pretty unique experience for me. So I'm glad I got this opportunity as well. So I'm going to speak about some joint work with several collaborators. I'm largely going to talk about this last paper I wrote with my student Chandramouli and Olga, who's a postdoc at ICTP. And I'll also discuss some previous work I did earlier this year with Alok, Siddharth, and Pushkal. And there are also some earlier papers that might be relevant for this talk. So before I start the main part of the talk, I just wanted to try and give you a sense of the rough story that I'm trying to get towards. So the rough story that I'm going to try and convey is that quantum gravity has a very remarkable property. And the remarkable property that I'm going to try and make precise in some settings is the following. That when you have a geometric setting of this kind, where you have some region R, which is completely surrounded by its complement. So, R is enclosed completely by its complement. Then it so happens that a copy of all the information that is available in R is also available in its complement. And that's what I'm going to refer to in this talk as the holography of information. Now, just to emphasize why this is surprising, you could contrast this with the situation in a local quantum field theory. In a local quantum field theory, if you took the same configuration of a region which was surrounded by its complement, then you could specify the wave function of the universe separately in the region and in the complement. In particular, you could place this yellow excitation in the middle of the region without giving any hint to the observer who lives outside that this yellow excitation has been placed. Of course, the observer could wait a long time for the signals to emerge, but the claim is that in quantum gravity, the observer doesn't have to wait and already knows, just by making measurements at the same time slice in this complementary region, that this excitation is living inside this region R. And that's the reason I think that this is a very surprising claim. Now, sometimes when I give this talk, and I've discussed it, I know with some of you, I think some people get the impression that this is some formal result about the theory. It's some formal result about the structure of operator algebras in quantum gravity. And the main thing that I want to do today, the main message in a sense that I want to convey today, is that this is not a formal result, but it's a very physical result. And perhaps the main technical point I'd want to make today is that this is a result that we can check in a completely controlled setting. So in particular, I'm going to spend some time trying to describe how, if you just take global anti-de Sitter space and take low energy states about the vacuum of global anti-de Sitter space, just low energy states, which is a setting which we think we understand a lot about, and you consider some set of observers who live in this brown annular region, I'm going to try and explain how these observers can obtain complete information about the state in the bulk of the space-time. And this is not going to be a result which is going to use any formal arguments. This is just something we can see very explicitly, as I'll try and persuade you. I will then try and make some more formal arguments, trying to argue how, if one goes beyond the low energy limit and looks at the full theory of quantum gravity, that such a result should hold more generally. And in fact, the same arguments, when they are applied to asymptotically flat spacetimes, tell us that all the information that is available on null infinity. So usually we think of the S matrix as being defined on null infinity, and that one needs to know correlation functions of operators on null infinity to know what the state is. But I'm going to I'm going to at least try and quote the result and explain very briefly why, in fact, all this information can be obtained from the past boundary of future null infinity, which is this red region here, or alternately, the future boundary of past null infinity, which is this orange region here. I think that this result has some implications for black holes that I'll describe at the end of my talk. The main slogan, in a sense, that this result gives for black holes is that the exterior region always contains a complete copy of the information that's in the interior. And that's perhaps a fresh perspective on how we should think about black hole information and how we should recover it. That being said, this is an overview of the rest of my talk, which I'll try and make some of these statements, some of these claims that I made more precise. As I said, I'm going to start this talk by explaining how these ideas work just in a very controlled setting at low energies in global anti-de Sitter space. And then I'll try and explain how we can extrapolate these arguments that one can check at low energies to the full theory in anti-de Sitter space. And then I'll mention very briefly how it also works in flat space. And then I'll conclude with some discussion about black holes. So let me start by describing how what I call the holography of information works at low energies in anti-de Sitter space. This is my setting. So we have a global ADS. We could be in any dimension, in 3 or larger dimensions in the bulk. And I'm going to start in this first part of my talk by considering just some low energy state in some theory of gravity that's coupled to matter. The matter could be string theoretic or could have some other degrees of freedom. It doesn't matter for the purposes of this argument. The state that I'm going to look at is a state that's well described by quantum field theoretic excitations in global anti-de Sitter space. So we think we understand how to analyze this system. When we know how to do quantum field theory in global ADS, we even know how to quantize gravity if you're just doing low energy physics. We know what's the structure of the states in the Hilbert space that we get. We know in global ADS, just because global ADS looks like a box, there is a vacuum, and then there's a gap to the next excitation, and there's some set of discrete excitations. The distance to this gap depends on the mass of the lightest field in the theory, and then there are other excitations which are gapped. There could, of course, be degeneracies in these energy eigenstates. There could be all sorts of degeneracies, but the vacuum is unique. And when I refer to a low energy state, what I'm referring to is that we live, we are thinking of a state in this theory, which is some linear combination of these states in the Hilbert space. So that's the kind of state that I'm looking at. Now, the point I'd like to make is that if we have observers who are confined to this brown annular region, so this is a Cauchy slice in global ADS, the state of the world is one of these low energy states. What I want to argue is that if you have observers who can make measurements on this Cauchy slice in this brown region, then these observers can detect what this state in the bulk is. Now that's the argument I'd like to make, but in fact, in a theory of gravity, you might start worrying about how you define these observers in this brown region. How do you make the definition of the brown region gauge invariant and so on. And because I don't want to think about those complications, rather than allowing these observers to explore this region on one Cauchy slice for some finite values of R, I'm instead going to push them all the way to the boundary and allow them to explore observables very close to the boundary, but for a finite time band, which is of size epsilon. And the way you should think of this epsilon is that if you think of the boundary of this region as being at some radius R0, then the relation between this R0 and epsilon is roughly R0 is cot of epsilon by 2. So if you make epsilon very small, then R0 becomes very large and vice versa. And of course, we have to keep epsilon smaller than the light crossing time of ADS. So this brown region doesn't expand to become the full Cauchy slice, but it's some order 1 but small number, which is some time band, some thin time band that lives on the boundary. And so I'm going to think of observers who are allowed to make experiments that last for this time. If you want, you can think of them as observers whose detectors are forced to switch off after this time epsilon and can switch on only at time 0. Okay. Now, what are the powers that these observers
could I ask, I can't really tell. Are you slipping something in here, or is this like really obviously equivalent, these two restrictions on what the observers are able to do?
I'm actually going to be on in everything I say precisely, I'm going to be on the right picture.
Is the right picture like obviously the same as the left, or?
It's morally the same as the left picture, but I don't want to say it's obviously the same. And in fact, the reason I'm in the right picture is because the right picture is more precise, I think. So okay. In the left picture, you would worry if you send something in, the boundaries of the region could fluctuate, and then you would have to worry about how those fluctuations behave. And that's why I don't want, on the left picture, which is the one which is, you have a Cauchy slice, you might worry about how the boundaries of the region fluctuate. And that's why I'll always be in the time band picture. I mean, that's a precise picture.
Oh, okay.
You could try and make the picture on the left precise as well. I mean, I think, if you're an empty global ADS and you're working in quantum field theory about a fixed background, then these two things are exactly the same. But once the metric fluctuates, these things are not exactly the same. And that's why I want to be in the picture on the right-hand side.
Okay.
But the question is, do you allow only simple operators in the boundary region?
Yeah, I'm coming to that next. Yeah, I'll come to that next. That's the next thing I want to say. So as you asked very correctly, the question is, what are the observations that we're going to allow these observers to make? Of course, we've known AdS/CFT now for more than 20 years, and if I allow these observers to do anything they like on the boundary, then the statement becomes content-free. And so I'm not going to allow them to do anything they like on the boundary, and that's because we live in low energy states, and they can get away by doing something much less than using arbitrarily complicated observations. And so here's what we are going to allow these observers to do, which is something I think is well defined in the bulk theory. Okay? So the first thing I'm going to allow them to do is I'm going to allow them to act with simple low energy unitary operators from the time band. For instance, if you had some bulk field, you could take the boundary value of this bulk field and then you smear it on the time band with this function f, and you act with this unitary operator on the state. So these observers live in the state, and then they are allowed to manipulate the state. And physically, once again, the cartoon way you should think about this is that these observers are creating some small excitation in the region that they live in. If you were working in a quantum field theory in a fixed space-time background, then this is indeed what such a unitary operation would do. It would create some excitation here. Okay. The other thing, and it's important because we do want to use gravitational effects here. The statement clearly could not work without gravity. The other thing these observers can do is they can measure the energy. The reason they can measure the energy from the boundary is because if you put some excitation in the bulk here, like this red excitation, you're forced to modify the metric far away. And these observers measure the energy the same way we measure the mass of the sun. And they can do this from the boundary due to the Gauss law. Okay? So they just, we allow them to measure the metric, the subleading components of the metric, with the leading deviations away from global anti-de Sitter space. And then they take this metric and they integrate it all over the sphere. So you need a lot of observers. You need a team of observers who can measure the metric at every point, and then they can add up their results. And they do this, and they are allowed to measure the energy of the state. Now, it's going to be important for the argument I make that these observers are allowed to apply the standard rules of quantum mechanics to this observable. So we are not in classical gravity. And when I say, in fact, when I use the word quantum gravity, what it means is that we should be allowed to use the standard rules of quantum mechanics for this observable, at least within the low energy effective field theory. If you're in one of these low energy states and these observers make this measurement of this integrated boundary metric, then this is some Hermitian observable. It has a spectral decomposition. And in quantum mechanics, they could get various values on measuring this operator. And the standard rules of quantum mechanics tell us that the probability that they will obtain the result E if the global state of the system is G is just the expectation value of this projector in the state G. In particular, one probability that I'm going to be interested in is the probability that they get 0. So, it could be that you're in some state which is not the vacuum, which is a vacuum plus some other states. And yet when you measure the energy, you get 0 because you're allowed quantum fluctuations of this kind. And the probability of getting 0 is the expectation value of this projector on this unique vacuum state in this global state G. And because these observers can determine this probability, this is something they can observe just by taking many identically prepared systems and by measuring the energy again and again and determining with what probability they obtain 0. Okay. So far, what I've said is pretty, I think should be pretty uncontroversial. Just to summarize, I said the observers can act with simple unitaries and they're allowed to make projective measurements of the energy, and they have access to identically prepared systems so that they can determine probabilities. So this is really the textbook framework for quantum information questions that we teach our students. So, this is the framework that I'm going to adopt.
Excuse me, when you say identically prepared systems, you mean the entire system?
The entire system. So one way to think about this is
so observers inside the ADS patch won't have access to experiments that were done in other instances of the same.
That's a very good point. So the way one should think about this is you can think of a big global ADS. Within that big global ADS, there are smaller regions, which you think of as local patches of global ADS. And you have these teams of observers who surround these local patches and they make observations in these different systems. And then they have to meet together and add together their observations.
Or you might say you have a large number of replicas of some kind of condensed matter system, which looks like a conformal field theory, and they're all in the same laboratory.
Yeah,
and
you could do
an
that.
experimenter
Exactly. So
in that laboratory.
That's another way to think of it.
Okay.
That you could have a lab system which simulates global ADS, and you have observers who are allowed to make these measurements, and then they add up their results. You know, the problem is that if we start thinking of cosmological questions of the kind you mentioned, where the observers can make only one measurement or they're inside the system, then we lose, I think, a lot of the framework of quantum information questions where we can determine probabilities. I kind of don't want to go down that path, and I want to take the standard approach where the observers are, in a sense, you're right, they're kind of external to the system, and that they can make these measurements and then they can add them over identically prepared systems.
And not
I think
just
it's an
measurements.
interesting question of what happens cosmologically if they're just part of the system.
Are you allowing them to operate with local Hamiltonians?
They will not operate with the local Hamiltonian, but they'll measure the energy. I'm going to allow them to measure the energy.
They're not allowed to operate with. Well, what I'm really getting at is what I'm wondering whether you give them the power, to run the Hamiltonian backwards.
No, I will not give them the power. I'll never act with the operator e to the IHT.
Okay, good.
But I will act with the operators e to the IOX, where O is maybe some field operator. So I'm going to allow them to add the Hermitian operator, some field operator to the Hamiltonian, and then they're allowed to measure the energy. So they just measure the energy. They're not allowed to evolve the full system forward and backward in time.
Good.
Okay, great. So far, as I said, this is a textbook framework. In fact, the reason to emphasize this is, as Lenny pointed out, you could ask in a cosmological setting whether the textbook framework is the right framework to use in a theory of gravity. And that's an interesting question which we can discuss, but I'm going to use it for now. Okay, so here's the first task. Okay? The first task is that I put these observers in some system G, in some state G. And then I ask them, there are these observers who live in this brown region. I ask them, is this global state of the world that you're living in, or the global state of the system that you have in front of you, is it the vacuum or is it not the vacuum? So is it like this empty picture on the left-hand side, or is it some picture that has an excitation like this picture on the right-hand side? Okay, so that's the question we ask these observers. So I want to emphasize, first of all, that this kind of a question is not possible to answer in a local quantum field theory. If you switched off all gravitational effects, then there is no way these observers could distinguish the vacuum from a completely orthogonal state, which is a bulk unitary operator acting on the vacuum, where the bulk unitary operator is an operator that lives in the middle of ADS. I want to emphasize that this is also the case if you're in a gauge theory, provided it's a non-gravitational gauge theory. You could take this unitary operator to be a small Wilson loop operator. You could act in the vacuum. You would get a completely different state. And these observers, these poor observers who live in this brown region, would have absolutely no way of distinguishing the state on the left from the state on the right. And the reason is that this bulk unitary commutes with every observation they can do. And so this is a task that I want to emphasize is impossible in the absolute.
Oh, wait, if the little blue dot was a charged particle, you would detect it by its Coulomb field.
Yes, so there are some states which the observers would be able to determine, but the question is that there are many states that they would not be able to distinguish from the vacuum. You see, you could of course have a state of the kind you mentioned, even in a scalar field theory, which is just some delocalized state, which clearly is distinct from the vacuum. But the point is that even in a gauge theory, you could take a Wilson loop and create a state which was distinct from the vacuum, and the observers would not notice any difference. So the challenge we have given them is, can you tell us whether the state is the vacuum or if it's not the vacuum? And they cannot meet the challenge in general in a local quantum field theory. Of course, in some special states, they can if the state is disturbed near the boundary. That's the claim. Okay. In gravity, yes. Is there a question?
Yeah, so is the point that if there was a gauge invariant excitation, then you can't figure it out, but if there is, say, a charged excitation, then you can?
Yeah, if there's a charged excitation, indeed, you can tell the charge and you would know you're not in the vacuum in gauge theory. But the gauge theories have local gauge invariant observables. So there are many states where you can't tell the difference. Yeah,
but then in the gravity setting, if I have a excitation in the center, shouldn't I address it with some Wilson line from the boundary where it says where that thing is sitting, because
So you can think of this as a manifestation of the fact that there are no local gauge invariant operators in gravity.
Mm-hmm.
So, you know, this is, in some sense, this is a statement we've made for a long time, right? That there are no local gauge invariant operators in gravity. And now I'm trying to say how you can exploit the statement to actually reconstruct the state in the bulk. So you're right. You know, there is no such operator like some localized Wilson loop that doesn't distinguish, that doesn't change anything near the boundary. And the reason this protocol works is because of that, because there is no local gauge invariant operator in gravity.
Thanks. Thank you.
Okay, thank you. So here's how the observers solve the problem in gravity. It's kind of embarrassingly simple. They just measure the energy. They measure the energy many, many times because they have access to these identically prepared systems. By the rules of quantum mechanics, the measurement of the energy directly gives them the expectation value of P0, this projector on the vacuum, in the state G. And remember, P0 is just bra 0, ket 0. So the expectation of P0 is just directly given by G0 mod squared. Okay? So if they have access to identically prepared systems, they just keep measuring the energy and they determine the probability that they're getting 0. If this probability is 1, they know the state is 0. If the probability is not 1, it's some other state. In particular, if you took one of these bulk unitaries and you acted on the vacuum to create an orthogonal state, then this probability would just become 0. And so in gravity, just by measuring the energy, they can tell these observers can successfully complete this task that was already impossible in a local quantum field here.
Okay. Sorry. So one question is, so do you really need an observer that can do things not locally and access the whole system together to measure age?
So the observers do need to be able to make measurements all on this brown region. So they need to go around it because they need to integrate the metric. But the physical
but
process
is it like many observers, each one has access to a part of this and then just need to classically collect the results?
That's one way to think about it. Or you could think of one observer who in identically prepared systems at one point makes a measurement here, the next system goes and makes a measurement here, and then makes a measurement here, and then goes around and then adds up the result of those measurements. But if it's
that's exactly my, I think there is a question there because the different terms in the Hamiltonian, like if I divide the system into small regions and then write the Hamiltonian as a sum over them, these terms do not really commute with each other.
So in gravity, they will, because this is just the integrated metric. So it's really literally the sum of the metrics at different on the boundary. So you just have to take the subleading term in the metric and just add up those metrics. So it's just a sum of different observables.
But can't we just say in the boundary theory, he measures the energy density, whatever that energy density happens to be?
Yeah, you could measure the energy density in the boundary theory. I mean, I kind of...
It does contain different terms, but that's okay. It commutes with itself.
That's right.
Well, it doesn't really, I mean, like any discretization will tell you they don't commute with each other.
Yeah.
And in other words, so your energy eigenstate, like the ground state, that's not the eigenstate of the energy density.
It is not an eigenstate of the energy density, exactly.
No.
But indeed, when you measure the sum, it will be an eigenstate of that observable.
Yes. But if you are measuring at every location and then you are doing the sum, then you actually get the eigenstates of the energy density operator, which.
But it's just the sum, right? So if you were in the vacuum, the sum would always be 0. It's true you might sometimes get positive answers for some things and negative answers, but it has to be the case. I mean, it's really just the sum of different observables. So you could just take these observables and look at the sum.
So I guess my point is, it's like if you want to measure total spin of 2 spin 1/2, then you can't do it. You can't do it in the first one, and then you do it in the second one because then you get the like SZ eigenstates or something. You don't get.
I understand. If the spins are entangled, then you measure so this is, it's not like, it's not if you're just measuring SZ1 plus SZ2.
Yeah, that's okay because it's
SZ1 and SZ2.
Yeah.
So the analog here is just SZ1 plus SZ2. They're just commuting observables. These commute in the theory of gravity as well because they're asymptotic observables. So asymptotic observables do commute at space-like separation, even in the theory of gravity. So these metrics that make up the energy really are just commuting observables. And you could measure SZ1 first and SZ2 later. And it could be that you found SZ1 to be positive and then you found it to be negative the next time, but you would always find the sum was positive.
Okay.
I don't, okay, so let's discuss more later, but I think this is actually a key difference between like a U1 charge and the Hamiltonian.
You want water?
No, it's fine. I'm good.
So is there someone has a question? It's the Hamiltonian written in a particular form. You know, it's the Hamiltonian written as a sum of a boundary metric.
Yeah.
So you know, there might be other ways of measuring the Hamiltonian that might be more complicated. But here I'm really, the way I'm thinking about this is you just look at the deviation of the metric from ADS and add it up. But you know, we could have a team of observers. I'm actually fine to have a team of observers who make a coordinated measurement at the same time, and then they add up their results. So we could do that.
I wonder if there could be some subtlety about I mean, the type of commutator that Xiaoliang is worried about is some kind of term which is only present for operators that are right next to each other. So like the energy density at points right next to each other in the regularization. And I wonder if there could be some subtlety in that the asymptotic limit of the metric equals the boundary stress tensor when you care about points that are only like one lattice spacing apart.
Maybe. Well, I don't know. I mean, it would be nice to make that more precise. It might be that, I mean, I can't think of anything which, I mean, I'm just measuring T00 and adding up T00, but there could be, you know, you could do something more elaborate. You could try and take some particle and look at its orbits or do something else to measure the energy. But it would be nice if if there's some subtlety which is important and somehow prevents us from measuring the energy, that would be interesting.
It does seem important that the Hamiltonian is not a sum of commuting local terms.
It is so I didn't understand why it's not a sum of commuting local terms. It's the metric which you add up and which you commute. So it's just T00 which you add up.
Let's see. If it was a sum of commuting local terms, wouldn't we just minimize the energy by minimizing all of those separate terms locally? And
exactly, that's the point. Yeah, like in the case of a charge, the zero charge state is just zero charge everywhere. Well, but in the case of Hamiltonian, you cannot write the Hamiltonian of a region and minimize it, and then the next region. Yeah.
I want to emphasize that this is not, you know, it's not. You're right about the bulk Hamiltonian, that there are terms which, I mean, maybe so maybe this is a good point. You know, you're right. If you look at the bulk Hamiltonian, it's indeed not the case that you can write it as a sum of one region plus a sum of some other region. So if you think of the bulk Hamiltonian, the fact that there is entanglement is very important, and that's why you come up with the vacuum state, which is smooth, right? Otherwise, you would just have disentangled states. But I'm not trying to measure the bulk Hamiltonian here. I'm just trying to measure the boundary metric. So
okay, if I think about the CFT, let's say CFT 1+1, then the boundary Hamiltonian shouldn't be a sum of commuting terms because the reason Douglas said. I mean, just purely as a boundary statement without using the holographic duality.
So that's
and I think that's related to like T mu nu is not a primary field. I mean, it has a different kind of OPE.
Yeah, it could be. So you're saying that there's a physical. You're saying there's a physical obstruction to measuring.
Yeah, there is a physical obstruction. If you have a CFT defined on a circle and you cut it into 10 parts and say, I want to measure the energy of each part as a quantum measurement, which means you get some eigenvalues of the energy in that region, and then you sum over them. Then you get different states from measuring the whole Hamiltonian and get an eigenstate.
That's what Douglas was saying about the stress tensor and taking points which are one lattice spacing apart and worrying about that.
Right. Yeah,
that's right. Okay. So you're saying we'll have to do a coordinated measurement of the energy. Okay, so we could discuss that more. So we could discuss more about how these observers measure the energy. So in some sense, what you're worried about is that if you have an observer here who measures the energy, this observer might disturb the measurement.
Exactly, because of the uncertainty principle. Yes.
Yeah. So you'd need some more coordinated global measurement that goes around. You'd need some way of smoothing this over large enough regions and then making a measurement of this kind. Yeah, okay, that's a good point. So I think you're right that we would have to, it's important, I think, to think of a good physical protocol for measuring the energy. I don't think in principle there should be an obstruction to measuring the energy in the CFT. We should be able to measure the energy. But I guess what your point is that, if you have a detector which is turned on right here, the detector might affect something which is slightly far away, which is right next to it. And so you have to be careful to smooth it out over long enough regions and then add those things. So I think that's a good point. And one should think more carefully about how you can measure it. I would think that one should be able to resolve that by taking detectors that are somehow large enough and that couple to a large enough region so you don't have to worry about this. But maybe it's a fundamental obstruction, which would be interesting if that is the case. Okay, so I'm going to assume though for the rest of the talk that it should be possible to measure the energy in that you should take the and maybe it requires like detectors which are large in space and you need to add up those results.
Could I also ask another question?
Yeah.
So how in your argument you said at least morally you have access to this annular strip all the way at asymptotic infinity,
right.
But how is it possible to say, for example, if I give you access to an annular strip which is not at infinity, like a finite radius in the bulk geometry, is that how important is that in your argument?
I think that's an interesting question. It makes things. I think it would be nice to make that more precise. I'll say something about that in flat space. If you're not at infinity, in general, I don't know how to make it precise if you're not at infinity.
Okay, thank you.
Yeah. Okay. So you might have said that maybe this task was too simple because the vacuum was uniquely identified by conserved charge. And you measured the energy, you found it was 0, and that uniquely identified the vacuum. So now we're going to give the observers a harder task. So let's say we ask the observers a more difficult question, which cannot be resolved just by measuring the energy. So let's say we take a simple Hermitian operator from this time band 0 to epsilon, and this operator is not necessarily a unitary operator; it's just a Hermitian operator. And this notation ket x means the application, the state formed by applying this operator to the vacuum. And now we ask the observers to determine if the state of the system that they live in is this x or whether it is not x. So it could even be the case that this operator x is related by a global symmetry to another operator. And maybe this operator x creates the red ball, and the other operator, which is related by global symmetry, creates the blue ball. And the observers now have to distinguish between these two states that have the same energy, whether the state G that they live in is the one with the red ball or whether it's the one with the blue ball. So this, again, is of course a completely hopeless task in a local quantum field theory for the same reasons that we discussed previously, that you could act with a unitary. In fact, you could act with a unitary in the bulk that changes the red ball to the blue ball in a local quantum field theory. And there's no way you would be able to distinguish from this brown annular region whether you had done that in a local quantum field theory. In fact, it turns out that in gravity, you can again do this task in a pretty simple way, and it's the following. So remember, this x was a Hermitian operator near the boundary, and one of the powers we gave the observer was to act with unitaries that were exponentiated versions of these Hermitian operators. So they don't need to act with a unitary for a large parameter, but they do need to act with a unitary which looks like 1 plus ijx. And if they do that, they're allowed to make this manipulation of the state. It's one of the manipulations we allowed them to do. So they take the state G and they modify it to the state which is the unitary acting on G. Sorry, I think I forgot to mention that for simplicity, I had taken this state, the state G that the observers now live in is orthogonal to the vacuum. So I've excluded the previous case where G had a component to the vacuum. And I'm now looking at states which don't have the vacuum. And by acting with this unitary, the observers now further modify the state from G to this UG, where to first order or second order in J, I've written down the expression on the board. And the protocol is that after making this manipulation, they then subsequently measure the energy and they determine the probability that they get 0. So you can compute what this probability is reliably in perturbation theory. And the probability is just given by the expectation value of this projector in the modified state. Okay? So just again, by the standard rules of quantum mechanics, you took the state G, you acted on it with this unitary, and now you measure the energy, and you ask what's the expectation, what's the probability of getting 0? And you can compute what that probability is. It's a very simple computation. And remember, because I said that G was orthogonal to the vacuum, this 1 doesn't contribute. When this G goes through from this 1 and hits the bra 0 here, that doesn't contribute. And so if you ask what this probability is to second order in J, this probability just gets a contribution from G and this term X acting on bra 0, and this X acting on ket 0 and again contracted with this G. And you see that that is directly given by J squared into mod of Gx, the whole square. So you see that once again with this very simple protocol, which involves acting with a unitary operator, which is not the Hamiltonian, but acting with some unitary operator, which was an exponentiated version of some Hermitian operator near the boundary, which could have been a field or something else which creates an excitation. And then subsequently measuring the energy and determining the probability of getting 0, they can determine the overlap of the state G with the state X. So the summary is that if the observers are placed in a state G, which is orthogonal to the vacuum, they can determine G of X squared, where this state X is the state produced by acting with some near boundary Hermitian operator that is accessible to the observers on the vacuum. So this is the second task that I told you how the observers could complete. In fact, this almost completes the story. And the reason it completes the story, because this set of states that you get by acting with simple Hermitian operators in the vacuum already form a basis for the low energy Hilbert space. So we were at low energies, and corresponding to that, we are allowed to act with simple operators on the vacuum. And in fact, it's not hard to see that the action of these simple Hermitian operators in the vacuum already generates all low energy states in the Hilbert space. So sometimes this, people get surprised by this result, but I want to emphasize this is really not a deep result. Okay? I really want to emphasize that this is a very simple result. And to emphasize how simple it is, I want to explain how this works just if you take an EPR pair. Okay? So if you take an EPR pair and you take some state which is an entangled state of 2 spins, then the operators on the first qubit, if you look at Hermitian operators that act on the first qubit, you can see that that generates a basis for the Hilbert space, as I've written down in front of you. You could take sigma z, 1 plus sigma z, 1 minus sigma z, sigma x and sigma y, where 1 means they act on the first qubit. And you see there are 4 such operators and they already generate a basis for the Hilbert space. Now, there are some obvious physical points. The first is that this doesn't violate locality. It doesn't violate locality because the observer acting on the first qubit cannot actually create one of these states, because physically we are only allowed to act with unitary operators. So unfortunately, we have these unfortunate terms in the language where we say you act with a Hermitian operator on a state, but you're never allowed to act with a Hermitian operator. You're only allowed to act with unitary operators. And when we say act with a Hermitian operator, it's just a mathematical application of a Hermitian operator to a state. So this fact doesn't violate locality. And secondly, this fact by itself obviously doesn't give the observer on the first qubit any information about the second qubit. And that is because all the unitaries on the second qubit clearly commute with all the observations you can make on the first qubit. So you make any observation, if the observer on the second qubit decides to act with a unitary, the observer in the first qubit is out of luck, cannot determine what that unitary was. So what we're doing here is actually the same trick. It's the fact that in a quantum field theory, in any quantum field theory, not necessarily in gravity, the vacuum has so much entanglement that in fact you can generate a basis for all states by applying Hermitian operators from this annulus or from this time band to the vacuum. So we can prove this formally, and in fact I'll mention the proof a little later in the talk, but for the purposes of the first part where I'm just for low energy states, this is something you can just check. You can check it numerically and explicitly. So in fact, as part of the paper, we have some code that does this. You can just take single trace operators and you can smear them with some functions, and you can determine numerically what's the right kind of smearing you need to have over the time band 0 to epsilon in order to generate all single particle states. And while we're within the regime of perturbation theory, you can also generate all higher particle states by taking multi-trace operators and smearing them with appropriate functions, again from 0 to epsilon. So this is simply true at low energies, that the action of these Hermitian operators near the boundary on the vacuum forms a basis. It doesn't require gravity. It's true in any quantum field theory. And now this actually allows us to complete the entire story, because the final task you can ask the observers is, you just put in some state G. The state G could have all kinds of excitations. It could have this red, blue, and green ball and maybe other kinds of excitations. And now the observers are asked to identify what the state G is. They're supposed to tell us without any priors what the state G is. So the protocol is actually quite simple. First, they need to make some preparatory moves. They need to act with a preparatory unitary to make this G orthogonal to the vacuum. They can always see if their unitary has succeeded, because as I explained at the beginning, they can measure the overlap of G with the vacuum. Then the protocol I explained gives them the overlap, the mod square of the overlap of G with a full set of basis vectors. And so all I need to do now to complete the task is to get the phase of G with X. This phase is actually not hard to get, and we explain how to do that in the paper. And the protocol is quite simple. You see, the overall phase of G is meaningless. So you can always pick the phase of G so that the overlap of G with some state XR, which is created by the application of the operator XR on the vacuum, is real. Okay, that's just a choice of convention. Now, because XR is a Hermitian operator, if you give me some other Hermitian operator X, XR plus X is a Hermitian operator. And the protocol I described allows us to measure mod of G of XR plus G of X the whole square. And because G of XR is real by convention, this also tells us the real part of G of X. Now, because I know the real part of G of X and I know the mod square of G of X, the mod square, this almost completely fixes G of X. It leaves a sign ambiguity in the imaginary part of G of X. We've explained in the paper how you can resolve this sign ambiguity.
Sorry, but to do this, you need a X to form a basis, which means there is exponentially many operator X you need to go through.
Sorry, can you say, I couldn't hear. Can you say again,
please? If you want X, the state X to form a basis, then you need to go over that procedure for exponentially many X.
Yes, you have to go over this procedure for many, many X, indeed.
And so most of them have very high energy, so they will get a big
exactly. So most of them have a small overlap. So it's important that we are careful about the errors that we have. So we deal with this issue in the paper. So let me just go to the next slide and I'll answer your question. So you're right. You're absolutely right that you know so this is this step here. The observers need to go over this procedure for many, many X's. And because if they go over this procedure for many, many X's, you might worry, you know, do errors pile up in this process because you went through this procedure for many, many X's. And so we also have a verification protocol. You see, in the end, the observers develop a guess for the state, and then they can do a one-shot measurement where they can determine the overlap of the state G with this linear combination of X's that they determined where these linear combination was these coefficients that they guessed at by their procedure. And if this overlap is 1, they know they've succeeded. If it's not 1, they know they've not succeeded, and they need to go back and do the measurements with greater accuracy. So we are careful about the errors that these observers are allowed to have. So, you know, in fact, the precise description of the task is that these observers need to determine the state up to some accuracy, which is given by this delta. They're allowed to make individual observations to some accuracy that's also controlled by this delta. And you're absolutely right that they need to repeat this protocol for many, many basis states. But in the end, there is a one-shot verification process which they can do to determine if they've, you know, got the correct coefficients or not, which is the same, which is related to the protocol I explained earlier. So there is a systematic procedure, and it's indeed true that they do need to go through this many, many times. I want to emphasize, however, that because we are at low energies, at no point do they need an accuracy which is order 1 over n. Everything here is an order 1 accuracy. So, you know, there are an order 1 number of states below some UV cutoff, which we put much below the Planck scale. The entropy, the total number of states below that is also order 1. So all the accuracies that we're discussing here are all order 1 accuracy, where the Planck scale or the ratio of the Planck scale to the ADS scale doesn't appear anywhere at all.
Could I ask?
Yeah.
So since you're talking about this interval on the boundary.
Yes.
Everything here could be stated just in the boundary language, right?
Just in the bulk language?
Just in the boundary language.
Oh yeah, of course. In the boundary language, you could state everything. Yes.
So we could forget, like, we could make a statement, forget about quantum gravity, just a statement about quantum field theory, that if you're able to measure something, then you can determine the state exactly. And the things you need to be able to measure are, you need to be able to compute the projector, the probability that it's in the ground state, and you also need to be able to measure, to be able to apply unitaries built out of some kind of restricted class of operators.
Right.
Is that right?
Right. In the boundary, you could do something better. You know, if you have access to, if you're really in the boundary CFT, you have access to all operators. So you could just pick some very complicated operator once and for all and just measure its expectation value.
But you're making
some operator which would give
right,
you one.
That's a trivial statement. You're making some statement which I just want to translate the statement that you've made here into 100% quantum field theory language.
Yes, you could translate. So the statement is that there's a restricted class of operators which are actually exponentiated versions of generalized free fields in the CFT and multi-trace operators of generalized free fields in the CFT. So those are the unitaries that we're allowed to act with, and then you're allowed to measure the energy.
That sounds like some kind of statement about a large M theory. Like, is the statement you're making not just something about quantum field theory?
The statement I made right now was a statement about a large N theory, because I mean, that was what I was translating into a bulk gravitational language. You could try and ask, I mean, you're right, actually. I mean, you could just take some completely random quantum field theory, and then by the state operator map, the set of all local operators would, generates a basis of the Hilbert space. And so if you're allowed to act with all kinds of unitaries and then measure the projector, you would get, you could determine any state. But as you said, that's kind of a trivial statement. So the interesting statement is you have a restricted class of operators, which are these generalized free fields, and you are allowed to act with unitaries, which are exponentiated versions of that. And that and the energy already lets you determine what the state is. If you were not allowed to measure the energy, you would not be able to determine the state in this setup. Yeah.
I'm trying to understand what the precise definition is of the class of operators you're supposed to measure in a more general setting. Like the generalized free fields is some approximate notion in a large N theory, but I feel like if your argument is correct, it should not only
in the most general setting, it would be all Hermitian operators. As you say, it would be a trivial statement.
Yeah, but so aren't you making a non-trivial statement that should mean something like you can get by with much less than that?
No, I think that the non-trivial statement is that if you are in a large N theory, then these exponentiated generalized free field operators are not enough to generate all projectors on states. Because if you really took N to infinity and you looked at these generalized free field operators in a large N theory, then that would not be enough without the measurement of the energy to determine the state. So, I mean, I think the statement becomes non-trivial when you think about it in a large N theory. Maybe there's another way to think about it in a general quantum field theory. But, maybe the bulk language is the simplest to think about it. If you are just in a local quantum field theory in the bulk, which is the analog of taking N to infinity, you just decouple gravity, then these observers can still act with these unitaries and can make measurements of generalized free fields near the boundary, but that cannot tell them the state. It's the fact that they can measure the energy from the boundary which helps them. And that's what's special.
I'm just trying to, I mean, if it's a statement in the boundary that only applies in some large N limit, then it seems like it should only apply in the bulk in like a G Newton goes to 0 limit. And
well, I think the statement is meaningful it's interesting in the G Newton goes to 0 limit. If you took a setup where gravity was strongly coupled in the bulk, then you would lose a lot of these notions of what one means by low energy and what one means by simple. And so if you started taking a limit where you took G string to be large, then, this whole thing would not be. So maybe the next part of my talk where I'll try and make a more formal argument will be more interesting. But as you say, it would then kind of degenerate into a trivial statement if you took G string.
Okay, so the restriction into the set of the non-trivial set of operators that you defined is a statement about the large N limit. And you say that in the large N limit, you can get by with fewer operators than you might have thought.
Yeah, that's right.
Okay.
That's right. So
yeah, thank you.
Exactly. Okay. So let me just say one thing that's interesting about this, the bulk gravitational theory. In the bulk gravitational theory, this suggests that, if you were to define, of course, there is entanglement between the annulus and the rest of ADS. But if you think of entanglement entropy as a measure of ignorance of the rest of ADS from the annulus, then provided you're allowed to measure the energy, the statement is that this entanglement entropy, if it's defined as a measure of ignorance, is just 0. And, usually we say we should restrict to some little Hilbert space or some chord Hilbert space of operators. But provided the energy is part of this little Hilbert space, provided you're allowed to take the metric and add up measurements of the metric, which as we discussed might be something we should think about more. Provided you're allowed to do that, you see, you can already in the vacuum tell that you're in the vacuum just by making measurements in the annulus. So you might have thought that in the local quantum field theory, there is some entanglement of this yellow region with the brown region, which is proportional to the area of the interface between them. But in the theory of gravity, that's not the case, because you can tell from outside in the vacuum that you are in the vacuum just by making this very simple one-shot measurement of the energy. And so I think that's an interesting statement, and I think it tells us, we'll come back to this again later, that there's something interesting about how to define entanglement in theories of gravity, which is not just a simple local correction over how local quantum field theories behave. Okay, I now want to, I spent some time describing this protocol in flat space, and as Douglas was saying, I think the interesting part of this protocol was you could work in bulk perturbation theory and do everything, in a bulk perturbation theory in a control limit. I now want to try and explain how you could make these extrapolations. So I'm actually again going to focus on ADS. And what I want to argue is that this low energy physical protocol, if you make a careful extrapolation, leads to the statement of the holography of information in the full theory. In a sense, this is something we already know because we've known about ADS-CFT for a long time. But the argument here is that if you had not known about ADS-CFT in some sense, you might still have guessed that a gravitational theory in the bulk was holographic by making these arguments. And of course, once I make these arguments, I'm going to go beyond my limit where I can work within a bulk quantum field theory about a fixed space-time background or with a fluctuating metric. So I have to be careful about what are the precise assumptions I make about the UV theory of gravity. And so I'll try and explain what those precise assumptions are. Okay, so the precise statement I now want to make is the following. I now want to say, so I've changed the color coding of my diagrams because I now want to consider arbitrary states in the bulk theory. And I want to say if you have an arbitrary state in the bulk theory, which could include black holes or could include some other arbitrary excitation, then such a state can be distinguished by an observable in the time band 0 and epsilon near the boundary. And this is an argument you can make purely in the bulk by extrapolating the arguments I made previously. And I'm now going to try and explain what are the assumptions one needs to make this argument. Okay, so here's the assumption. I'm going to kind of go through the same argument, but now being more precise about what's true in the full theory. The first assumption one needs to make is that the vacuum, we assume that in this full theory of quantum gravity in the bulk, whatever it is, there is still a notion of a boundary metric, and there is still this observable, which is the integrated boundary metric. Now, I do not want to assume that this integrated boundary metric is the full Hamiltonian of the theory. But I do want to assume that it still gives me an accurate reading of the energy, at least for low energy states. In particular, the assumption I need to make is that if you measure this integrated metric and you find that the answer is 0, then this tells you with reliability that you're in the vacuum of the full theory. So this is, you could think of it as a statement that you cannot hide energy in a theory of quantum gravity from the boundary metric. If you have an excited state, then you are forced to deform the boundary metric in some way. And I want to emphasize, this is not the statement that this energy can distinguish between two black hole microstates. Maybe it can't, but what I do want it to do is be able to accurately distinguish between the vacuum and some other state. And if this is the case, then this projector on the vacuum that I was talking about is an observable in this boundary time band, even in this full theory of gravity. The second assumption I need to make is that it should be possible to formulate the theory in the space given by exciting the vacuum by these boundary operators, but by boundary operators at arbitrary times. So this is the assumption that if you start with this vacuum and then you throw in stuff from the boundary, like these red things I've thrown in here, this should generate for you all states. Now, sometimes, people who work in gravity ask, why should that be the case? Why shouldn't there be stuff, which was just formed autonomously in the bulk? And the reason this is a good assumption is because this Hilbert space that I formed is manifestly closed under time evolution. And the reason it's manifestly closed under time evolution is that if I do time evolution, I just move these disturbances up and down in time. And therefore, just unitarity cannot force us to include any more states in the Hilbert space. The second reason this is a good assumption to make is that this is quite a large Hilbert space. And in particular, it accommodates all black holes that can be formed from collapse, because we know you can throw in stuff from the boundary and form black holes. So I think this is a good assumption to make, and this is the assumption in which the argument I make will hold. Okay. Now, if you grant me this assumption, then in fact, you can prove using formal arguments. Of course, you can't check numerically like I did previously, but you can prove using formal arguments that you can generate the same Hilbert space by acting with operators from a small time band on the vacuum. And the way this argument goes is by using the analytic properties of this matrix element between a state and an operator and the vacuum. If you take some state that was generated by the process on the left, and you consider this matrix element, this matrix element is non-zero for some value of t, because this state was generated by acting with this operator at some value of t. But you can check that this matrix element is also an analytic function in the upper half t plane. And therefore, this matrix element cannot vanish for t being in this small time band, because if it were to vanish, because it's analytic in the upper half t plane, it would vanish everywhere, which is not possible because the state n was created by the action of such an operator. And therefore, there is no operator in this larger Hilbert space that's orthogonal to all operators that can be created by acting with a smaller set of operators. Okay. So this is a formal proof of the statement that I made previously, that you can squeeze the Hilbert space and generate all states by acting with operators in the small time band on the vacuum. Okay. Now, as I emphasized previously, the fact that you can squeeze the Hilbert space is true also in a local quantum field theory and does not give any bulk information by itself. But there is a unique property of gravity, which is that the vacuum can be identified from the boundary in gravity, which I emphasized already a few times in this talk. And when you combine this trivial property of a local quantum field theory on the left-hand side with this property, which is unique to gravity, you find that boundary operators in this small time band contain all the information there is about the bulk. And that argument is very simple to make, and it goes as follows. Let's say we have some operator in the theory. You expand it in your favorite basis of states. So this is what I've done in the first line. By the argument that you could squeeze the Hilbert space, each of these states can be generated by the action of an operator in the time band in the vacuum. Now, therefore, you can write this operator in this form as a linear combination of an operator in the time band acting on bra vacuum, operator in the time band acting on ket vacuum. But this operator in the middle, which is just the projector in the vacuum, is itself a boundary operator in the theory of gravity. And what you have on the right side is a linear combination of a product of 3 operators. And because all of these operators belong to this algebra we are talking about, this linear combination of a product of operators also belongs to the algebra. And this is a formal argument that you could have made about the algebra of operators in the time band, which would tell you that the bulk algebra of operators in this time band always contains all information about the bulk without assuming ADS-CFT. Of course, in ADS, we kind of know this result because we know it from other reasons. But you can apply the same kinds of arguments to flat space. So I'm not going to go through the arguments in detail because I'm running a little late. But let me just try and tell you what the results are. The same kinds of arguments, when they're applied to flat space, lead to the conclusion that all information about massless particles that you might have thought is spread all over null infinity, which is this cone on top you see here, can in fact be obtained by observations that are made in this red time band. And once again, you can try and set up physical protocols where you could say, what if you have a shock wave that's going to come and hit the later part of null infinity? What is the observation you need to do in this little red band to determine what the form of the shock wave was? And there is an answer to that. There are specific correlators you can measure. We wrote them down in the paper, but it's very similar to the ADS procedure, which will let you determine what is the form of the shock wave without actually making observations at that later part. And the assumption, sorry, I should say one more thing actually before I go on to this. There's a question I think that Prahar asked earlier about, is there a situation where you can say something about without going to infinity? So in fact, in flat space, there is an interesting setup of this kind, where I tried to argue, I quoted to you, I didn't argue to you. I said to you that, in flat space, if you're on future null infinity, you can reduce all the information on future null infinity to this little red region. But in fact, you can do a little bit better. You can reduce all the information to the future of a cut, so like to the future of this violet cut, to the information on the cut itself. So there is a sense in which information on later cuts is a proper subset of information on earlier cuts. So you can think of this as a statement that this red band is all the way out at infinity. If you think of null infinity as being a sequence of Cauchy slices that tends upwards, you can think of this red band as being the outermost boundary of that Cauchy slice, and these other bands as being inner boundaries. And at each state, the statement is that the inner boundary, the boundary knows about what's happening inside it, if you think of the region to the top as being inside it, but doesn't know about what's happening outside it. So this is one example where you can make this precise without going all the way to infinity. You can try and say how a region, how the boundary of a region knows what's happening inside it. Okay. So I won't go through this in detail, but just to say the assumptions that go into proving these arguments are pretty similar to the assumptions I made in ADS. The key technical difference is that in flat space, in 4-dimensional flat space, as Andy and collaborators have emphasized to us many times recently, the vacua are not unique, but they are infinitely degenerate. You have all of these supertranslation, these vacua that are distinguished by their supertranslation charges. But all of these supertranslation charges also live near this past boundary of future null infinity. And therefore, you can try and make the same kind of argument you made in ADS, although it's a technically more intricate argument that you need to make. Okay, can I, maybe I'll go on for 5 minutes more. Is that okay, Xiaolang?
Yeah.
5 or 10 minutes. Okay, thanks. So let me just spend maybe 5 or 10 minutes saying what I think this says about black holes. Okay. So I think that this perspective that I'm trying to present, I think leads to a different way of thinking about black hole information. I think one often tries to ask the question of, how does information come out of the black hole as it evaporates? That's the question of how, if you collect Hawking radiation on this green slice, can you obtain all the information about the black hole? And of course, that is one way to obtain information, where you allow the black hole to evaporate and you collect all of its Hawking radiation. But the arguments that I've been giving you suggest that even before evaporation, if you make measurements on this red region, you can already obtain information about the state inside the black hole. Of course, if you wanted to distinguish different microstates, you would have to make very complicated measurements. But in fact, simple estimates suggest that the measurements you need to make on this red region are no more complicated than the measurements you need to make in collecting the Hawking radiation. You need to use a different set of effects for which gravity is important, but you could obtain information just by making measurements outside the black hole without waiting for it to evaporate. There is a formal way in which you can state this result, this statement that the information is always outside. And once again, it's a statement you can make by looking at the von Neumann entropy and interpreting the von Neumann entropy as a notion of ignorance. So it's very common to define a state on Scri+, that's the state by this thick red line here, and ask how the von Neumann entropy of the state varies as you extend this thick red line up to infinity. Okay? And one way to define this von Neumann entropy, or the standard way to define the von Neumann entropy, is to look for a density matrix, which is an element of the algebra of null infinity that lives up to this red line, and ask what is the right element of the algebra, so that when it is traced with some observable B, gives you the correct expectation value of the observable B in the state of the system. But by the arguments I quoted to you in flat space, you can always choose an element of this bigger algebra to be some element of the algebra from the smaller region right near the past boundary of future null infinity. And therefore, you can just once and for all choose this density matrix to be some operator from here, from the past boundary of future null infinity, independent of this U. And therefore, this S, which you define as trace of rho log rho, is just independent of U. And that would tell you that if you were to plot this von Neumann entropy as a function of this algebra on this cut, then this von Neumann entropy just doesn't depend on U. The reason I have a finite intercept here, and I'm not saying it's 0, is because in this analysis, I didn't include massive particles. But apart from that, all the information you were going to get about massless particles and null infinity is already present in this fast boundary. Now, I want to emphasize, and sometimes when I give this talk, there are questions about, could you get the page curve by restricting the algebra in some appropriate way? And I think the answer to that is yes. In fact, there are, if you were to, for instance, throw out the energy and the mass from your set of observables, which is a thing you can do consistently at Scri+, then that would give you the physical or the mathematical analog of physically collecting the Hawking radiation. And perhaps this restriction of the algebra, where you decide to close your eyes to some gravitational degrees of freedom, will yield the page curve. But the point I want to emphasize here is that there is a physical point, which is that if you were to allow yourself access to all possible observations you can make outside here, then the information is always outside the black hole. And that's what is given by the fact that this von Neumann entropy is a constant. Okay, I should say that this is not inconsistent with the recent work, a lot of it done at Stanford, which derives the page curve for an ADS black hole coupled to a bath. And the reason is that in those setups, the Hilbert space by force factorizes into the Hilbert space of the black hole and the Hilbert space of the bath. And so it's clear that both the bath and the black hole should follow a conventional page curve. But I think that there is an important difference between the setup where you have a black hole and then gravity stops being dynamical beyond some point, which is the setup in which all of these calculations have been done, and a more realistic setup where you have a black hole and you have weak gravity beyond a region. And I think in a setup where there is gravity literally stops being dynamical beyond some point, information may really emerge only after some page time. But if you ask fine-grained questions about information, as we're asking here, then weak effects in gravity, as I emphasized in the first part of my talk also, can conspire to give very different answers from local theories. And I think therefore for a more realistic black hole where gravity is dynamical all the way out to infinity, the more correct statement would be that the information is always outside. Okay, so I'll stop here. I'm sure we can have more questions. Let me just summarize the main message that I wanted to convey. The main message I wanted to convey is that in a theory of gravity, the information about a region is also available outside that you see in this cartoon. In a local quantum field theory, you have an excitation in the middle of this region. The observer outside doesn't know whether the excitation exists or not. But in theory of gravity, you're forced to modify the geometry outside. And the observer outside can, by using clever effects, determine whether this excitation exists or not. And I did, in the later part of the talk, give some formal arguments about operator algebras, but I do want to emphasize, which was the first part of what I said, that these are not just formal arguments, but these arguments lead to a very concrete physical protocol to extract information at low energies in ADS. So it's not just some argument about operator algebras, but it really is a physical effect about gravity. And I think it offers also a fresh perspective on black hole information. So I'll stop here. Thank you for your attention.
Thanks very much. Any questions?
Oh, sorry, I missed it. Could you say what observables you have to leave out to get to see the page curve from the
you have to throw out the Bondi mass. I didn't say it very precisely, but if you look at the algebra on null infinity, the way you divide it is you have the Bondi mass, which is one component of the metric, and then you have the news operators, which are another component of the metric. So in some sense, in a physical sense, these appear on the same footing because they're components of the metric. So if you were to measure the Riemann tensor, you could extract the Bondi mass, or you could extract the news operators. But because the operator, because the OPs at null infinity, it's literally a free theory as opposed to ADS, it's possible to just forget about the Bondi mass. And the reason is, if you measure news operators, you keep multiplying news operators, you will never generate the Bondi mass back in an OPE. And so you could just forget about the Bondi mass. And if you did that and you closed your eyes to that part of the metric, then you might get a page curve. I think even there's an interesting question in 4 dimensions about the entanglement between the infrared modes and the entanglement between the soft and the hard degrees of freedom. But I think the common feeling in the community is that that's not a significant effect. And if that's not a significant effect, if there's not much entanglement between the soft and the hard degrees of freedom, then you would get a page curve.
So there's just one thing you have to throw out.
I beg your pardon?
Just one variable you didn't have to keep track of to get the page curve.
Yeah, so there are different components of the metric. There are 2 components which you could call dynamical, and you could throw away one component of the metric. So I mean, it's you'd have to throw out the Bondi mass at every value of u, but you'd have to throw away. It's like throwing out G00.
I see.
In ADS, I don't know how to do that, because you could say I won't measure T00. I won't measure like the 00 component of stress tensor, but it doesn't work because it keeps getting generated. So you take like other dynamical fields and you take the OP and you'll generate the energy in the OP.
Yeah, I suspect I suspect that you don't need to throw away it completely, as long as like the measurement you did is not accurate enough. Like when the error goes to, like if instead of P0, you have a projection to an energy window, and that energy window has some finite, I don't know, either finite energy or proportional to system size, then it's equivalent to removing it.
Yeah, you could do that, but the problem, and at least if you're discussing black holes, is that you have to make exponentially accurate measurements to reconstruct the microstate. So you would have to say that you're not allowed to measure one component to any accuracy. So one component you have order 1 accuracy, but for all other components you have exponentially high accuracy. So that sounds, I mean, you could do that mathematically, as I said, but it's a physically unnatural thing to do, because you're saying that.
So you mean if I don't do that, then I also won't get the page curve. I just get the entropy growth.
Then you'll just get the conventional Hawking curve. That's right. So if you don't measure things to high accuracy, then you'll just get the conventional Hawking curve. So you do need to have high, I mean, it's mathematically consistent. You could say there's some components of the metric which I measure very accurately and other components I don't. But physically it seems more natural to measure everything to the same accuracy.
Well, but so actually a related question, going back to the slides before this one, where you say just the previous one. Yeah.
This one? Yeah.
Yeah. So you're saying like no gravity is different from weak gravity.
Yes.
And I think that's suggesting that when I take the G Newton goes to 0, like if G Newton is very small, then it must be like measuring the P0 might become more and more difficult, because it will go back to the case with no gravity. So how do I see that it becomes more difficult?
Because that's a very good question. So let me say 2 things. So if the protocol that I described in the beginning, where you had low energy states, of course you could have made the same measurement just by waiting for the signals to emerge. For waiting for the relationship between the metric that you measure and the energy has this factor of G Newton in it. So if you take G Newton goes to 0, then the metric is not, so then it becomes harder and harder to determine the energy by variation of the metric, because you have to measure smaller and smaller deviations in the metric. So that's where G Newton appears. And indeed, it's the case that if you're in low energy effective field theory, you could take G Newton to 0 and you could just forget about these effects. But in gravity, I think the situation is more subtle for the following reason. You see, in a black hole, the entropy itself scales with G Newton, with an inverse power of G Newton. So if you wanted to reconstruct for a black hole the information outside, you would need an accuracy which was e to the minus s. And if you started taking a limit where G Newton goes to 0, this accuracy would also go off to infinity. So for black holes, it's not clear that there is a consistent limit in which it's easier to get information by looking at the Hawking radiation than it is by measuring these effects. For the low energy states that I mentioned at the beginning, it is clear, I think there is a limit in which it's much easier to get information by directly measuring the fields and waiting till ADS time. But for black holes, I don't think there is such a limit. Or at least I don't know of such a limit where it's much easier to get the information by measuring radiation than by using these effects that I described. I can say more about that if you have, I mean, I don't know if I answered your question, but I can say a few words more about it. So, you know, one way to think about this is you think of a small black hole that evaporates in anti-de Sitter space. There's a boundary dual of this process, which is you crash some gluons together or some glue balls together, and you form some small lump of quark gluon plasma and then evaporate it. And you could ask, you know, what if I wanted to reconstruct the original state of the glue balls? Is it easier when the quark gluon plasma exists, or is it easier when it's evaporated back into glue balls? So, you know, there is a naive thermodynamic argument you could make to estimate that difficulty. And the estimate of the difficulty is when the quark gluon plasma exists, the difficulty somehow scales with the entropy of the quark gluon plasma. After it's evaporated back into glue balls, the difficulty scales with the entropy of the glue balls. But remember, the entropy of the final glue balls is always larger than the entropy of the quark gluon plasma because of the second law of thermodynamics. So it always becomes harder and harder to reconstruct the state, not easier. So if you look at a small black hole from the boundary point of view, it's kind of clear that if you wait for the black hole to evaporate and collect the Hawking radiation, it's no easier to back calculate the state than it was when the black hole already existed. I mean, if it was easier, it would be a statement that the system is unthermalized. It's somehow become easier to recover the information than it is at intermediate times. So for a small black hole, you know, I think these weak effects, of course, they're hard. You need to make accurate measurements, but I don't think they're any harder than these measurements of waiting for the Hawking radiation. The estimate I gave is not a precise estimate. Maybe there's something wrong with it. But I think the naive estimate is that this process is no harder for a black hole than the process of collecting the Hawking radiation.
So taking this example of a small ADS black hole, like naively, as you emphasized in talks previously, there is also no page curve. If you just follow the global state on the boundary, right, you just get a constant entropy, right?
That's right.
But there, in order to separate a subsystem from the boundary theory, it's not just we are measuring some metric or deleting some components of the metric. I mean, there are many, many, many other operators in the n=4 super Yang-Mills or whatever it is. So in the flat space case, I'm not sure the Bondi mass or the other components of the metric are sort of enough variables, you know, to just describe the state. Like in the ADS case, they would just correspond to the values of the stress tensor point-wise. But we know there.
Yeah, I never said certainly that the one-point functions of the stress tensor, one-point functions of Bondi mass would give you all the information. You would have to measure correlators of the Bondi mass with other insertions of the metric. So you'd have to measure the algebra, which involves up to S insertions of all these dynamical fields. So, you know, and that's, you would have to do for measuring the Hawking radiation as well. You'd have to measure S point correlators of these news operators.
But not just the stress tensor, right? To measure the information of a small black hole, I also might need some correlation functions of non-stress tensor operators.
Yeah, you could probably get it just from this. So let me say two things. In ADS, you could probably get it from the stress tensor because you'd start generating everything in the OP. So, you know, if you just measured arbitrary point correlators of the stress tensor, you would probably get maybe even all information. Not in ADS3. In ADS3, the TTOP closes. But in higher dimensional ADS, you might just get all information. But let me just say something. In flat space, actually, the story is much cleaner. Because in flat space, the structure of the Hilbert space at null infinity is literally that of a Fock space. And if you were to measure all the massless fields and just measure arbitrary correlators of them, you will really get all the information that you have. So, you know, you might have said, you know, what if you have some D-brane operator Why don't you, what if you have a D-brane state? Why don't you need a D-brane operator to get this information? But there is no D-brane operator you need at null infinity. You need operators of the massless fields, and you produce these D-branes by throwing together these massless fields. But the Hilbert space is completely described as a Fock space. And there are additional massive particles that live at future infinity, which I haven't discussed at all. And so we could discuss about how much information is in those massive particles. But as far as the massless particles go and the operators which are well defined at null infinity go, those are really just polynomials of the massless fields in the theory. But even in ADS, if you think about it, if you looked at high enough points of the stress tensor, you would get you would get everything. So the fact that this is true in flat space is not so surprising.
Subrat, could you explain the squeezing?
Yeah, sure. Yeah, I can explain the squeezing. I want to emphasize the squeezing is kind of a trivial statement if you believe in ADS-CFT. It's a statement that this slide. It's a statement that if you act with all operators on this time band, you will generate all states. So it's kind of
I thought we were just using. Wait, sorry. In the previous step, we were acting, let's say, with simple operators at different times.
Yeah, so by this step, yeah, okay, so let's talk about simple operators, and let's talk about simple operators at different times.
So are you saying that simple operators at just one time is equivalent to simple operators at all times?
Yeah, simple operators in a small time band is equivalent to simple operators at all times. So maybe for this, I should go to a previous slide. At this level, I was not at maybe I should go to this slide.
In this state, making that statement, I mean,
here,
one way of making that argument, there's sort of a trivial argument along those lines, which is that the Hamiltonian is a simple operator. So,
no, it's not that argument. It's the following argument. It's an argument that, so it's this argument. So let's say you took a one particle state, right? And you wanted to get some energy eigenstate out of it. So here's one way you would do it, right? You take some simple operator, which is a generalized free field. You'd integrate it over the full time band over length pi, and then act on the vacuum with it. That lets you create a certain creation operator. But you can do the same thing by integrating over a much smaller time band, 0 to epsilon. And this doesn't involve. This is the fact that if you wanted to get the positive Fourier components, you can. So if you have a big function over some interval 0 to pi, and you just want another function that has support only on 0 to epsilon, but which shares the same positive Fourier components, you can always find that. So it's kind of a statement in Fourier analysis that
this sounds. It's okay. I'm trying to understand what. I mean, okay. Here's the kind of thing that's bothering me is: suppose we start with some kind of high energy state, and then we act with just one operator at different times.
Mm-hmm.
We can create an enormous number of states that way, like e to the s number of states that way.
So here in this situation, so we have to decide if you're talking about simple operators or complicated. Let's talk about simple.
Let's just say that we're only going to act with one operator at different.
Yeah, and let's be about the vacuum. So let's even be about the vacuum.
Okay, but then I need two operators. One operator to create the high energy state, and then the other operator to act with at different times.
Well, so we have to decide if you want the formal argument or let me say this argument, which already may be somewhat surprising, which is just an argument in QFT where we're just acting with one operator on the vacuum, and then we can go on to your case. Is that okay?
Okay.
Already on the vacuum, so now you have a time band which is only of length pi. You can't act beyond pi. It kind of is periodic. So you have only the interval 0 to pi to act on. And you might already have said if you act in the interval 0 to pi by 10, how do you get the same states that you got by acting in 0 to pi? And that you can do very explicitly. And the reason is that when you smear things with this function w of t, which has support only from 0 to epsilon, when you smear this O of t, you'll get creation operators from O, and you'll also get a whole bunch of annihilation operators. But those annihilation operators, just kill the vacuum. Okay, so now we could go on to your case where you had like a multi-particle state. So of course, if you're still you're looking at low energy states or simple operators, then you could play the same trick for multi-particle states as well. Like you could act 2 operators or 3 operators, and you'd keep getting the same thing. But maybe the situation you want to look at is a black hole microstate. Is that what you wanted to look at?
I want to take a high energy state and then I want to act with just one operator at different times and get a huge number of different states that way.
Yeah. So you want to take a very high energy state and act with a.
Yeah, it's like a black hole microstate, and then you apply some small perturbation, then it's thermalized after some time. So then you could take the time t after thermalization, and then that t could be
the claim was not, by the way, that you could take a simple so I think that if you wanted to take a simple operator and act it on the same microstate, yeah, so if your initial let's see. So first of all, the claim I made was always about lifting things from the vacuum. So it was always that you have some operators, you act them on the vacuum, and you can act with some other operators in a smaller time band in the vacuum.
Well, we can start with the vacuum if you want, and I can use my first operator to inject a lot of energy, and then use my second operator to create lots of states.
So now the back reaction is going to be important. This state you're creating is not like some state in the Fock space.
No.
Good. So I think the statement would still be that if you took, I think the statement would still be that there is no such, I mean, I think it's this argument. So we can go through this argument. It's the fact that, so this operator A of t now looks like O of t1 and O of t2, right? And I think the statement would still be that any state you created by acting with, say, two operators at some point of time, maybe separated by some region, you could create the same state by acting with operators in a small time band. And maybe your point is that you would need to wiggle these
or acting with what operators in a small time band?
I think the same. So let's say you took the stress tensor and you acted with it at two different times, maybe T1 and then once again at T2.
Okay.
So the statement is you could then, and T1 and T2 were like widely separated. And the reason you could do that is because the first time you acted with it, you created a high energy state. And then you're acting with it once again at a later time. That's the example you wanted to consider, right? Yeah, I think that the argument is that you would indeed be able to get the same state by acting with the 2-point functions of the stress tensor in a smaller interval. But you're right that you'd probably need to wiggle your smearing function in some crazy way. So if the point is that if you do this, you will need to act with some very fine-tuned operator in the smaller interval to create the state. So if that's the point, I agree with that. But I think this argument would still be true. I mean, it's a very simple argument. It's the fact that if you look at this operator n was created by acting with two stress tensor operators at two values at the time, T1 and T2.
You take a linear combination with extremely large and canceling coefficients of the states with the operators at very slightly different times.
Yeah, I don't know about extremely large, but yeah, oscillatory coefficients. Yeah, you need some
so the other way of asking the question is, this squeezing, will that require, like when you decrease epsilon, will that require a higher and higher accuracy in your measurements in the operators in the epsilon window?
Yeah, absolutely. That's correct. So in the first part of the protocol, where I was careful about being at low energies, I should, it's important that my epsilon is some fraction of pi, some order 1 fraction of pi. So if my light crossing time of ADS is pi, I don't want to take epsilon to be 1 over n, but I want to take epsilon to be maybe pi over 100. So then it's indeed true that you need, your complication increases by a factor of 100, but it increases by some factor of 100. In the more general case, then, you're right that the complication could increase by a much larger amount, because if you have some black hole microstate, you could create it by acting over a very long time. And now I'm trying to create the same thing in some very complicated way. And so this is a formal argument. The statement is these operators still exist in the algebra. But this part of the argument is a formal argument because of what you said, that, there's something you could create over a very long time band in some simple way. And now you have to use some very highly oscillatory coefficients to create.
But does this argument, are you interpreting this as saying that it means that somehow all the information about the state is just contained in the information about measuring the operator in the small band?
No. I want to emphasize this, maybe this slide. Sorry, let me emphasize this slide, this one. The argument that we're discussing right now is literally just this argument. It's an argument about qubits. What you're saying is, if you have some very entangled pair and you take like some very complicated setup, then can you generate all states by acting with operators on one part of the system? And the answer is yes. And if the entanglement is very complicated and you acted with you're looking at some state which is very far away from the original state, then you may need to act with very complicated operators. But this statement that I'm making right now is just a statement about quantum field theory. It's the statement that you see in front of you, which holds for 2 qubits, where the statement is by acting on 1 qubit, you can generate all states in the Hilbert space. And this does not tell you that all the information is present in the first qubit. Clearly not. Because you act with a unitary on the second qubit, and that's completely invisible to the person on the first qubit. And also this doesn't violate locality, because we are not allowed to act with operators. Observers are not only allowed to act with unitary operators.
So could you remind us how this squeezing argument somehow led you to the conclusion that all the information was contained in the simple operators in some small strip?
No, it was the squeezing argument and the fact that you could project onto the vacuum. So maybe I should say again, is this fact. Is this part, this blue part was a squeezing argument, which is that applying the boundary operators to 0 generates the Hilbert space. Maybe one way to think about this, which may be more familiar, is to think of the state operator map. When we read the state operator map in Polchinski's book, Polchinski tells us that all operators at one point acting on the Hilbert space at minus infinity.
Yeah, no, all operators that we don't want to talk about. The interesting restriction you're making is simple operators. Like
is simple operators, indeed. So
that statement you won't find in Polchinski.
Indeed, but simple operators to create simple states. So this statement that I made, that simple operators create simple states, is also true in local quantum field theory.
Well, but you can make all operators create all states by acting with simple operators at very late times.
Just to say that the simple operator corresponds to simple states, and I didn't understand the question.
But if you're able to act with simple operators at late times,
yes,
then you can make states that are no longer simple.
Okay, so if you're allowed, well, okay, that's true, but the restrict. So let me again divide things into 2 messages I want to give. The first part was where you're acting with operators where the back reaction is small. So then this thing that you said doesn't apply. All the states are just well described by states which are some states in some approximate Fock space. Then you could say let's act with simple operators at arbitrary times. And then it's indeed true that you could act with simple operators also in a small time interval and generate that. And I think, well, okay, you wouldn't find the statement in Polchinski, but I think it's not, it's a statement that if you act with arbitrary polynomials of the stress tensor also in the vacuum, you would again generate all kinds of states. I mean, it's really just that statement.
But yeah, I'm just trying to, I guess that statement feels like really unphysical because it's going to be crazy superpositions of states that I wonder if, it seems like it doesn't mean that the information is there in the measurement of the simple
Indeed, it doesn't mean the information is there, because by itself, this statement is also true in the local quantum field theory. And that's why this information, I mean, this statement we're discussing right now, we could just discuss in a quantum field theory and just forget about gravity.
But can't we have the whole discussion in quantum field theory just in the boundary? Like it's simpler for me if we just think about everything in the boundary, and then we are having a conversation about quantum field theory.
Well,
and the statement, yeah.
Yeah, let's see. If we just say something in the boundary, yeah, I mean, we could say something in the boundary, and maybe the statement there is that, yeah, indeed, if you're allowed to measure the energy and you're allowed to measure simple operators in some, as we discussed, in some large N theory, then you can get away with fewer observations than you might have thought you needed. So you could make this. I mean, the statement, if you're not in large N and you want to make the statement in the boundary, it's kind of a trivial statement. So maybe if you should be at large N, and then we could have said, you might have said that, I have these large N fields and they don't satisfy some dispersion relation. And so it looks like I should have degrees of freedom that correspond to specifying the wave function on the full Cauchy slice in the bulk, which is like specifying the wave function on the time band from 0 to pi for these large N generalized free fields. And I'm saying that actually I can get the information from a smaller region if you also allow me to make measurements of the energy apart from these generalized free fields. So if you include the stress tensor and include the fact that energy is positive, the same information also lives in this time band 0 to epsilon. Okay. So, I mean, if you wanted to have the discussion in the quantum field theory and not make it trivial, then I think you would have to go to large N. but I do want to emphasize that you know, the fact that you generate all states in the Hilbert space you know, by acting with operators is a statement which would be true in a QFT. I mean, when I wanted to make this argument in the formal case, I wanted to make it to try and argue that, you know, there's a certain bulk Hilbert space you can construct in a physical process by exciting the vacuum at all times, which I think people who work on gravity would also agree with. And then I wanted to say you can generate the same Hilbert space by acting with operators in a small interval. And if you believe in ADS-CFT, it's kind of a trivial statement. But you know, if you didn't believe in ADS-CFT and you only knew about bulk gravity, then you might be surprised that that's the case. But I mean, in any case, that by itself doesn't tell you that all the information is there. It just tells you that you can generate states, and then you need additionally this fact that the vacuum can be identified, which is the physically important thing in the bulk. I'm answering your question, Douglas, or I feel I'm not answering your question.
I think so. I just need to. Oh.
I want to de-emphasize the left part. You know, maybe sometimes the left part might be surprising because we don't often discuss it this way. But I want to emphasize the part that's special to gravity, which is the right part, which is that the vacuum can be identified from the boundary. I mean, the left discussion we could have in a local quantum field theory, and it would not tell us that information about the middle is available near the boundary. The fact that you can generate all states is not the same as you can detect all states. And you may be able to generate all states, but there might still be unitaries which commute with every observation you can make. So the important thing, the physical point is you can detect all states, which is true only in gravity. And it's true because you can select this specific state, which is a vacuum. And that's the physically important point, I think, in gravity. So I do want to de-emphasize the left part, but I mean, we could discuss the left part. It's an important technical thing, but it's not, I don't think that's the key physical point. I think the key physical point we should focus on is the right one, which is that you can select the vacuum in some special states in gravity.
And by the way, measuring, okay, so another comment about measuring energy. I think, so there was this problem about whether different parts commute. But there's another thing is measuring Hamiltonian. Like if I measure the operator that's Hamiltonian,
yes,
is very different. Is very different from measuring the P0. I mean the projector.
So measuring
the projector to a particular energy.
P0, yes. But I just wanted to measure.
Is very in a local, and it's like if I expand it in terms of local operators, it's going to be very complicated.
It is, and indeed that's how we first discussed it. But I want to emphasize that in this protocol, you measure the energy and you just have to measure the probability that you get 0. So if you're allowed to measure the energy and you're allowed to apply the Born rule, then if you just wanted to measure the expectation value of the projector, that's easy to measure because it's just given by the probability that you get 0. So you know, at least in the first part of my talk where I was talking about this physical protocol, I really just wanted to use this projector just to get the expectation value. So if you look at this, for instance, you know, I was just measuring the expectation value of the projector. And that's actually just the same as repeatedly measuring the energy. So you don't have to add the projector to the Hamiltonian or, you know, have some von Neumann process for measuring the projector. You just have a von Neumann process for measuring the energy, and you get various answers and you determine the frequency with which you get 0. And that's the expectation value of the projector. And that's all we needed in this process. So that you're right, that if you try and expand the projector as a local operator, it looks very complicated. And indeed, in one 2016 paper, we did say that because, you know, we were ourselves uncomfortable with the idea that you should be able to do the simple process to get information in the bulk. But I think the correct way to think about it is that you just keep measuring the energy and look at the relative frequency, and that gives you the expectation value, and that's all we need.
So imagine I have like a single particle excitation in the middle of the bulk, and then right. I change it a little bit in a way that doesn't change the energy at all. So like it's like locally rotating a spin. That's because yes. there's different states with the same energy.
Yes.
And in that case, then, so let's say in that case,
this would still work. So exactly as you said, you see, the energy would be the same. So that's why this protocol is not just measuring the energy. you're right. There could be degeneracies in energy states. So if you just try to measure the energy, you would not be able to do things. So in particular, imagine that the state X was related by a global symmetry to another state. So that was the example I gave here. So, you could have this red particle and a blue particle, and they're related by global symmetry. So maybe there are no global symmetries in gravity, but I don't need to assume that for this talk. So let's say we believe there is some global symmetry which relates the red and the blue particles. So they have exactly the same energy. So just a measurement of the energy cannot distinguish them. But when I measure the correlators of the energy with other operators near the boundary, so there is one field which creates the red particle and another field which creates the blue particle. And when I measure the correlators of the energy with that field near the boundary, those correlators can distinguish for me these two excitations. So you're right that just a measurement of the energy will not work, but I need to measure, correlators of the energy with other observables, and that does indeed give me the information. Even if you have global symmetries, which cannot be distinguished just by energy.
Have you tried, so I'm wondering whether we can take the simple case like 2D and then think of something like a SYK model. And then it's a little bit different from the Largian series where everything is singlet because there is a fermion that's not an SUN singlet. But I guess that's the fermion field is what we consider as a simple field, a generalized free field. So I'm wondering whether the statement is like if you know a small interval of the correlators of the simple fermion operator, then you know the state. And that sounds true because of course you can get the energy you can get the Hamiltonian from it, and then
Yeah, I think it should be true. I think you should. We didn't do this in SYK, but this numerical verification we did as you said, there are two states, there are two parts. One is being able to measure the Hamiltonian, and the other is being able to generate the states. Generating the states, we check numerically. This is in higher dimensional ADS. This I think is ADS 5. But I think we could do the same thing. You could take a Green's function for the SYK and check explicitly. You can generate all these simple fermion states. And then if you can measure also the Hamiltonian, then I think you would be able to get the information. But it would be nice to check it more explicitly, you're right. Yeah, that's maybe one case where you could make this explicit as Douglas was saying, purely in the boundary setup. You just take the SYK model, take some simple operators, look at the measurements of energy and measurements of simple operators, and see if you can get all excitations of simple states. Yeah.
Does anyone else has their questions? Okay, if not, let's thanks Sharath again, and so officially let's end the talk here, but feel free to stay and talk more if Sharath still have time. Yeah, thanks very much.
Thank you. Yeah, thanks for coming by. Yeah, it's